Thank you, Alan. My name is Tim Rattay. This is the talk. It's the extra 5 minutes, which is my 5 minutes. I'm a clinician. I'm actually associate professor in breast surgery at the University of Leicester. This is a talk, case study that's based on a Horizon Europe funded project for which we are collaborating with Guido here, and also with Alan and Andre from Chentai, who are leading this track. So this is really about using Explainable AI to predict treatment side effects, and I think Alan has set the scene very nicely with his introductory talk, because this is in clinical medicine. Obviously, using AI is coming hard, thick and fast, the use of AI. But what we need is we need to be able to trust the AI, and doctors, but not just doctors, but the most important thing is patients. They will want to know why certain models will predict them at risk of, disease or a certain diagnosis, but in this case, a side effect from treatment for which we can do something about. So we're going to cover in this talk, it's just going to be me doing the introduction. The rest is all going to be Guido. You'll be complete relief to know, because this is obviously a machine learning conference. But that's what we're going to cover. So this area, this case study, is in the setting of survivorship. So cancer medicine, breast cancer is the cancer that I work with, or I see patients for, is a high surviving cancer, and that thankfully the 10-year survival in Europe is now about just under 80%, which means that of all 4 in 5 of the women with breast cancer will expect to survive at least 10 years. And there are currently 12 million breast cancer survivors in the WHO region Europe. This is not the European Union, but Europe itself. And in the UK, there is an estimate that currently there's about 800,000 survivors, people who have had treatment for breast cancer, but that's going to grow to 2030 to 1.2 million. So there's a lot of patients out there, or previous patients, who potentially could have side effects from their treatment while they've been cured of their cancer. And this is a very important initiative, particularly in the UK. There's the Living with and Beyond Cancer initiative, but there's similar initiatives all across European healthcare systems. So one of the things that, so we already use, I'm a surgeon, but I refer my patients to radiotherapy, of course, after surgery. And so AI, or machine learning, is sort of already implemented in the radiotherapy planning workflow. So as you can see on the left of that slide, we take certain parameters, patient details. The radiation oncologists will know about the treatment that they have to give to the target volume and target organ, and they will they have a planning CT scan at the beginning, which they use to contour their organs at risk, as well as the target volume, which is the cancer or the basin in breast surgery, or the breast, because usually it's after surgery, on the adjacent lymph nodes in breast surgery. And there's already some AI or machine learning being used in that system, because some of the contouring is semi-automated. And that way the radiation oncologists, together with medical physicists, they will be able to prescribe a treatment plan for that patient, and then a number of those patients, because of the effect of radiotherapy on the normal tissue, not just on the target tissue, that they have some of the radiation gets scattered to the normal tissue, they will that will can cause some side effects, both in the short term, but also the important ones are the long-term side effects, which is what this talk's focused about. So the idea of the PREACT project was to improve on. So when we talk to patients, we normally talk to them about the risk of side effects in general, based on general study data. For example, if we're talking about this is about lymphedema, this talk, if we say to a lady, if you have axillary node dissection, plus you also have radiotherapy to your nodal nodes above the clavicle and the nodes under your arm, and as well as the chest wall, your risk of long-term arm swelling is about 1 in 4, so 25%. Now, these are general risks based on trial data. But what we want as clinicians for our patients is to improve on that precision, on actually have the predicted risk for every patient individually. So this is about prediction modeling, and what the idea of the PREACT project is to use to train AI models on existing data from existing research studies, which Guido will talk about a bit more about, to generate models with a built-in explainability layer, because that way we'll get the trust of the patients and the clinicians when they discuss these predictions in the clinic, and they would be able to use that information to modify treatment. They may not necessarily modify the radiotherapy target volumes. They may a little bit maybe modify their plan to spare the normal tissues. But we also what we also will be introducing as part of the PREACT project is we'll be testing these models in a clinical trial where the patients who are predicted at high risk for lymphedema, which is the side effect of radiotherapy as well as breast surgery, arm swelling. We'll be able to use that. We'll be able to evaluate those models, which Guido is building at the moment, and we'll talk about in a minute, with the built-in explainability layer and a web interface, etc., in a trial to give the patients who are at high risk some supportive treatment, because there are some data that shows if patients wear an arm sleeve, which is a stockinette, which is worn for treatment for lymphedema, if you wear that preventatively for 3 months from the start of your radiotherapy in those at high risk, that can reduce the risk of arm lymphedema in the long term, which is the aim of this. So here's some pictures really of radiotherapy toxicity, of side effects from treatment. At the top left, you can see a patient, a lady who has had a reconstruction, and she's had some fibrosis, scarring, and atrophy of the breast. Then the radiotherapy, these are quite the severe examples, the moderate to severe examples, which we're trying to prevent. The majority of patients who have radiotherapy will get fairly mild side effects or sometimes no side effects. We're trying to identify the patients at high risk. Up to 20% will get sort of moderate side effects. And then in the middle picture, you see somebody with severe scarring and also dilated blood vessels called telangiectasia. And the bottom picture is what the subject is of this case study, which is which is the swelling of the arm, the chronic arm swelling, which is quite debilitating to patients. The patients think that to the patient that's actually quite a debilitating side effects. When we see in our clinic, they need to have massages, they need to wear these stockinettes, and they can have increased risk of infection. They're not able to use their arm very well. So it is a very important scenario. And now I'm handing over to the machine learning expert.
Good afternoon to everybody. So here we are training a data set with supervised learning. We have tabular data, and we are using ensembles of models. So we use random forest, gradient boosted trees, and also ensembles of multi-layer perceptrons. The problem with ensembles is that we are losing the explainability, especially with decision trees. I will talk later about decision trees, but just to remember a few things, we can introduce, in general, propositional rules like this one, x1 greater than t1 being a continuous constant, and x2 less than t2. With such a network, you can see this is a small multi-layer perceptron with a step activation function. There are many possible ways to introduce propositional rules like this one. It's just one rule. But here, what is important is that with this configuration of weight, we have a propositional rule. And in general, from a neural network, we would like to explain what is going on inside with propositional rules. In the history of multi-layer perceptrons, feed-forward neural networks, at the beginning, explainability was tackled by, in the majority of the works, by propositional rules. At the beginning of the 90s, even at the end of the 80s. So there was a small community of researchers trying to generate propositional rules from multi-layer perceptrons. Okay, so now the difficulty is that we can have weights, the parameters weights here we have. Here we can see simple values like 1, -1, 100, 0. But in general, weights have any values. And the difficulty is that the knowledge embedded within a neural network is complex, is entangled in all these activation values in all these weights. So I'm showing here the models more precisely. You can see here with this small multi-layer perceptron, H1, H2 have a step activation function. And in that case, we know exactly where are the discriminating boundaries. You can see here a full line. So can I point? Maybe? Yes. So here we have a propositional rule where H1, H2 have 1 for the activation value here. And so we have two classes of samples, black circles, white squares. And the discriminating hyperplane is passing on this value, minus W10 on W1, because we have a step activation function. Okay, this is a particular case. It was achieved many years ago. And then it was generalized into this model, which is called discretized interpretable multilayer network, which is a multilayer perceptron. The difference with respect to the previous slide is that we have a staircase activation function here, which is a generalization of the step function. And this staircase activation function generalized the sigmoid usual activation function that we have in multilayer perceptron. Okay, we could have other activation function, but you can see here the sigmoid activation here. And with that, we can find where are the discriminatory boundaries. And from them, we can generate the rules because we know where they are. Yes, another thing is that the connectivity here is not full. It's similar to 1D convolution in that case. 1D convolution with size of filters equal to 1. So if we have a 1D input layer, it's 1D convolution. If we have 2D convolution, 2D input layer, it's a 2D convolution of size 1. Okay, and with that, oops, sorry, was too fast. So here is the approximation of the sigmoid function. And before, with the step activation function, we had just a possible discriminatory boundary. With many stairs, we have many possible discriminatory boundary for each variable. A backpropagation algorithm was defined with this type of activation function, so it can learn any problem. And so any rule extraction algorithm has to determine where the discriminatory boundary are real or not. Are they present in some places or not? And from that neural network, you can generate propositional rules like this. For instance, we have the condition. Here in general, we have the inputs, x1, x3, xx. We have a threshold. And on the row, we have logical, so these are conditions, so it's a logical AND between each condition. For instance, here you can see that the first rule covers, in the testing set, 54 samples. There are no errors. Here we have, on the testing set, 1 error here. 19 are correct, and so on. This is the accuracy. We convert number of correct samples into accuracy. We have 2 classes, and so on. Then you can give what is the accuracy on the testing set, what is the fidelity. We'll come back to fidelity later, which is this is an important notion. Intuitively, fidelity gives how many times the rules correspond to the model decision. The decision is a class 1, class 2, or whatever. And here it was quite close on the testing set, quite close to 100%. It was only one sample where rules and the model didn't agree. Can give other statistical measures like what is the accuracy when rules and network agree. So if we exclude the samples where they disagree, you can see here that the accuracy is 82 on 83 cases where there was the fidelity. Okay, so this can be performed with this kind of DMLP network. Now, what happened when we put ensembles of multi-layer perceptrons? So in the past, we trained these multi-layer perceptrons with bagging. And when we combine them, we lose the interpretability. But in general. But with this type of model, we know whatever the number of layers, we always know where are the possible hyperplanes. So it's possible with a rule extraction algorithm, which is a heuristic algorithm. I will come back later on that, to determine the rules. Here we have another model, decision trees. What do we have? We have variables. So we have the root, then we have nodes, and for each root we have a predicate. Here the question is x1 less than or equal to t1 or greater than t1 and so on. If this is true, we go on this side, otherwise we go on this side. It's a binary decision tree. They are used very often with tabular data because they are fast to train and also because it's easy to translate them into propositional rules. If you follow a path from the root to a leaf, you know what is the decision, the reasoning behind that. So here on the leaves, you see what is the decision class. We have C1, C2, and so on. Okay, now, again, if we put trees in an ensemble by, for instance, majority voting, or a linear combination of decision, we take the average of probabilities, for instance, or for instance, with neural network, we could imagine a nonlinear combination with other layers after the single models, and so on. We also had in the past supervector machines that were very successful with tabular data. They are still successful. In general, the layer of weights between the input layer and the first hidden layer is frozen. It can play the role of a normalization layer because for each hidden area in the first hidden layer, we have a connection from an input neuron and a connection from the bias virtual unit. And it can do simply Gaussian normalization or min-max normalization, whatever you want. So this layer is frozen, then we train by SVMs. And then we apply rule extraction, as with the AMLD neural networks. At some point, I was interested to know if we could extract rules from ensemble of decision trees, because as they lose their interpretability, then I say, okay, I can transform each decision tree in several rules. Then I can insert these rules into a DMLP network. And then all the rules that are extracted from an ensemble of decision trees, like a random forest, can be translated into ensembles of the AMLD neural networks. And this was performed in 2018. I can show here the reference, the second one. So we transformed train random forest, gradient boosted trees into ensembles of the AMLD networks, and from the AMLD neural networks, we're able to generate propositional rules. Well, a bit later, we tried also this technique with simple convolutional neural networks in sentiment analysis. This is the third reference where we define a simple convolutional neural network, and we generated rules explaining how sentiment analysis decisions were performed. Essentially, we determined what were the words in a tweet which were into any propositional rule. And then later on, in 2020, we also applied to convolutional neural networks with 2 convolutional layers. So in a melanoma problem, classification, diagnosis of melanoma. So this can explain how we arrived to a decision of healthy or not healthy patients. Now, well, these were the old rule extraction techniques we defined for the AMLD networks, ensembles of neural networks, ensemble of decision trees, small convolutional neural network, and so on. Now we define a new rule extraction technique, and here I describe a bit what we did. So FIDEX is a local rule extractor. When I say local, it means that with respect to a unique sample, we generate a propositional rule explaining this sample. So again, the precise, I mean, the key idea is to determine exactly where are the discriminating boundaries, and we define a heuristic algorithm, and its algorithmic complexity is it's proportional to the product of the dimensionality of the classification problem, the number of training samples, the maximal number of rule antecedents per rule, and the number of stairs in the staircase activation function. With the previous rule extraction algorithm, it was global. I mean, we had to use all the training set. When a training set is big, it takes too long to generate the rules. With FIDEX, we can generate quickly a rule for a given sample. And the key idea, as I said, is that we know where are the discriminating boundaries, as I showed in this slide before. Since we know where they are, and they are parallel to the axis of the input neurons, we can define heuristic algorithms. In general, each step of FIDEX is based on improving the fidelity. At each step, we select, we have the whole list of all the discriminating boundaries, and then what you are doing is to find out where is the best one according to the criterion of fidelity. What is the boundary that will increase the most fidelity? And we iterate on that, and the purpose is to reach 100% fidelity for the training samples, and at the moment it's always possible. And from FIDEX we can define a global rule extraction algorithm. Essentially, in FIDEX we call many times FIDEX, which is a local algorithm. We call FIDEX, and then we discard after, suppose we have a training set with 1,000 samples, 10,000 samples. We call FIDEX 10,000 times for each sample of the training set. Then we obtain 10,000 rules, and then we start to discard rules that are not necessary, and then we obtain a global decision rule set that has less rules than the size of the training samples. For instance, this is unpublished work at the moment, so I submitted a paper recently where it was applied to tabular data with benchmark problems. Here it was applied to breast cancer, Wisconsin, well-known problem with a few hundred samples. We did cross-validations, and here we can see several models. RF is random forest. Random forest ORE is old rule extraction algorithm to compare with. GB is gradient boosting of trees. GBOR with the old rule extraction. Then we have quantized supervector machines. It's a supervector machine from which we can generate propositional rules. With linear kernel, with Gaussian kernel, and then the two last rows are with respect to ensembles of the AMLPs trained by bagging. BTOR is the old rule extraction algorithm. And then we can see for each column first test accuracy of the model, the fidelity of the rules on the testing set, the rule accuracy when rules and model agree. When only with the rules, the first rule accuracy, then the second rule accuracy when the rules agree with the model, the average number of rules we generate, and the average of conditions per rule. Okay, here just to show an example. There is no best model, let's say, for test accuracy. The highest accuracy was given by random forest with old rule extraction, and so on. But fidelity, you can see on this benchmark problem is quite high. It's above, in most of the case, above 98%. And of course, it is 100% on the training set. Okay, this was only just as an example. Now we come back to lymphedema, where we applied ensemble of decision trees and ensemble of neural networks. So we had 32 features. You can see the side effect with the arm, as was said by Tim just before. Okay, here we have an incidence of the positive class, what is interesting us, of only 6%, which is quite typical in medicine. So our training, our data set has a bit more than 6,000 samples, and positive class has an incidence of 6%. Here are the results that we obtain. Here we compare the AMLP ensembles, random forest, gradient boosting. You can see the AUC curve, the area under curve performance, which is for the gradient boosting 83.8 with a standard deviation of 0.2. So this is based on cross-validation. 83.8 is the AUC. At the moment, we are quite happy with that. Now, the next question is for the PREACT project. What do we want as false positive rate or true positive rate? Because we are discussing with several partners about that. We don't know which point on the curve we want at the moment. And this will finalize in the next month. Anyway, regarding explainability, here we have some comparison. We have a decision threshold which is varied. The decision threshold is important with respect to how many true positive do we want with respect to the false positives. When the decision threshold is quite low, 0.5, we generate, of course, more rules because the decision boundary becomes more complicated as we favor the positive samples. The fidelity is quite high on average on testing sets. And you see at 0.05 for the decision threshold, the true positive rate is 81.7 with a standard deviation of 2.9, and the false positive rate is 27.1, which is quite high. So maybe we prefer the second row. We don't know at the moment. Okay, and some rules that can show negative or positive. You can see, for instance, that weight, height are important. There is, in the state of the art, there is a relationship with incidence of lymphedema and BMI, which is the index of obesity when it's above 25. So we can see features like nodes involved. It means was the tumor in that place at some point. So in the negative, we tend to see that the nodes involved are low, whether in the positive roots they are higher. IMRT is the type of radiotherapy, intensity modulate radiotherapy. So in that case, we can see a rule, a positive rule with tomotherapy. You can see, for instance, the last rule, which is not the majority of the case. In some case, when the weight is quite high, more than 100 kilos, 102.7, and the mean heart dose received, so the irradiation received on the heart is above a given threshold, then we have positive patients. But we have many, many rules, so this is just a small sample. Anyway, physicians say that, well, it's possible, it's interpretable. Okay, some concluding remarks. So here we presented FIDEX and FIDEX Glow, which are local and global rule extraction algorithms that can be applied at least to ensembles. We are also applying them with convolutional neural networks, but it's still unpublished. Here we generated predictions with ensembles for the lymphedema problem. And in the future, we will have a web application for doctors to have a prediction with patients for a clinical trial and with explainability with local and global rule sets. Thank you for your attention. Any questions?
Questions? Yes, thank you very much for your presentation. It was very interesting, especially for me as a AI interested person. Some technical questions. All your machine learning models seem to be quite close. So it seems like there's no difference if I choose random forests, SVMs, bagging, boosting. It was quite surprising. Another question, you said that trees are a disadvantage or they hinder explainability. This was quite surprising for me because I would just formulate it the opposite way. When I look into hidden layers of networks, and on the opposite, I have a decision tree. The decision tree with real decisions is very much more explainable to me, at least when it is quite shallow, as you said. So I think I lose the explanation when I get bagging of hundreds of decision trees and I can't compare them. But with boosting, for example, when I have small decision trees and they are concatenated, chained, I think it's not the worst which we get out of normal models, is it?
So if you have hundreds of even small decision trees, it means you will have a lot of possible rules. Then if they are combined with, for instance, with linear combination of the probabilities, what are the rules by linear combination? I mean, 0.2 of this rule plus 0.3 of this rule, it's not very interpretable. And this is also the case with majority voting. Then your first question was on the AMLD ensembles.
If there's really not a real difference of which machine learning model I choose for the explainability.
Well, it can happen depending on the data set. In this case, the performance was quite close, and it happens. Yeah.
Okay. One question, you showed some graphics showing true positive rates and false positive rates. Maybe I misunderstood something, but I had the impression that the false negative rate would be the most interesting, isn't it? So I think the most high risk is that the machine learning algorithm says, you have not a high risk of radiotherapy, but there is a problem afterwards. So I think this would be the most human interesting number, isn't it?
Yes, the risk with selecting negatives that we don't select the positives. So with two classes is equivalent, negative or positive.
Okay.
It's equivalent because it's symmetrical. Some sense.
But I think, yes, you're right. I think from a clinical problem, a medical problem, we always don't want to do a diagnostic problem or a prediction problem like this. We don't want to miss cases, particularly in a diagnostic problem. This is a prediction problem of a side effect, but it's not, it's not in terms of cancer cure, but it's still, we don't want to miss cases because it is still a debilitating side effect to the patient, yeah.
Yeah, so I was wondering if you're familiar with the rule fit algorithm, because my impression was that you're first fitting a model, then later trying to explain the prediction of that model. But for example, the rule fit algorithm would already, include the rules and the selection of important rules in the whole fitting process. It would use a sparse set of rules, and also then later you could look at the importances of the individual rules. So I wonder, are you familiar with that approach, and have you compared that to your approach?
So you're asking if we insert the rules and then we see what...
if you are familiar with the rule fit algorithm and
rule fit, yes.
and how that would compare to your approach.
Yes, I did some comparison not on this problem with rule fit. If I remember well, rule fit extract a linear combination of the rules. It's you have a rule base, and then the decision is combined with a linear combination of selected rules. And to me, this is less interpretable than what we are doing, because a linear combination of rules, if you say 0.3 rule times rule 1 plus 0.2 rule 2 and so on, to me is not very clear.
But it gives you a weighting of the influence of the rules is already included.
Yes, but here you obtain, you can have several activated rules, and it's not a linear combination of these rules.
Thank you.